This video is lesson 8. We're up to our second to last lesson for the derivatives unit. And here we're going to take a look at logarithms and exponentials and how we can do derivatives with those. And just like we did with sine and cosine, I want to just do this one just kind of for fun with my graphing calculator to see if I can get it to teach me what the derivative of e to the x would be. So e is that very, very important number in math that's between 2 and 3. It's irrational, it's around 2.7-ish. And I want to see if I can find out what its derivative is. So I'm going to be playing this game like we did with sine and cosine. So I'm going to put in e to the x for my main function. And then my derivative, I'm going to have it graph that. So I'm going to say, hey, math menu, option number 8, numerical derivative of that y1, please. So I'll just go to my variables button, slide over to y variables, choose function, and then number 1. So it'll do the derivative of whatever's in y1. Yeah, that's my exponential right now, comma, and then I put in x because I was using x's, and then most importantly, x to say, please redo this at every pixel that you're at. Now I'm going to actually tell this to graph it a little bit thicker, just so that I can see which one's which. And I'm going to change my window instead of just the standard one. I'm going to make it kind of look like what I see here. I want to make it go up a little bit. So I'm going to change this to a maximum of around, 15. And watch what happens. So here we go. Here's the graph of e to the x. Yeah, it looks like a hockey stick. And then here comes its derivative. So this is now the derivative of e to the x. And this is the neat thing. It is exactly the same function. It just graphs right on top of e to the x. So it's not a proof that that's true, but it's just a little visual confirmation that it is actually the same thing. So we've got not only the function y is equal to e to the x here, but then when we asked our calculator to do the derivative, it just went and put it right on top of the old graph, just like that. So here was y prime, right? Same thing. Maybe not an equal sign. How about a nice big arrow? So if you have y equals e to the x, that one exponential, this only works for e to the x, then the derivative, y prime, is actually, or you can write it this way too if you want. Hey, let's do a derivative of e to the x. The answer to that is e to the x. Okay, it's exactly the same thing. The function is its own derivative. This is the only function other than y equals 0, which is pretty boring. It's the only function that does that is its own derivative. Okay, let's try another one out. What about the natural logarithm, the one that uses base e, right? It's just how that one works. All I have to do is go in here, change this to ln x, and I'm going to get it to regraph it. I think zoom 4 would probably be fine. Let's see what we have. So this first graph, that's ln, and oh, I think I broke it. Give me 1 second. Oh, sorry about that, just had my calculator in the wrong mode. I think it's ready to go now, so I'm just going to go zoom 4. There's ln x, and then here comes its derivative. And the question is, will we recognize this function? Yeah, it looks like it's got a vertical asymptote at the y-axis and then a horizontal asymptote on the x-axis. It's actually the graph of 1 over x, or at least half of the graph, right? Just the branch that's over on the positive x side. So on our notebook here, we've got, okay, y equals ln x right there. And then the derivative ended up being 1 over x. Just went just like that. So there's y prime. So if you have y is equal to ln x, this only works with that kind of logarithm, then y prime, otherwise known as, the derivative with respect to x of ln x, it's actually just 1 over x. Okay, I want to do one more though, just kind of foreshadowing for some work we're going to do in a later chapter. What about the derivative of ln of minus x? And you might be thinking, wait a minute, from what I know about logarithms, you should never put negatives in. And that's true, but what if the x's were negative? Then if x was negative, then the stuff going into ln, it's what we call the argument, it would actually be positive, so the graph should show up. It's just going to reflect the old graph around the y-axis. And so right here, this is my ln of opposite x. And let's see what the derivative of that actually looks like. So we'll just change this to opposite of x, please. And here we go. So there's the graph of ln x, but reversed, and here comes its derivative. It actually turns out it's just the other half of 1 over x. It's the other branch of 1 over x. So if we go to graph this, it's the branch that goes like this, through the point -1, -1, and then down like that. There's y prime. So it's also equal to 1 over x, just the other part. Okay, well, I guess we can maybe leave a little note on that. We can say, yeah, if you're doing that, y prime would actually also be 1 over x. But let's see if we can find another reason for why that's true. Maybe we can get there based on the chain rule. What we saw just 1 minute ago, maybe 2 minutes ago, is that the derivative of ln x, okay, this middle thing on your page, the derivative of that is 1 over x. All right, well, if I know that the derivative of ln x is 1 over x, it looks like I've got a blob going on here, little interior function. What happens if I exercise the chain rule on this? Then I would see that my derivative is going to be y prime is equal to, well, it should be 1 over that argument, 1 over opposite x. But that was cheating. I just pretended negative x was x, and it's not. So I should multiply by its derivative, but that would be a -1. And yeah, of course, the negatives cancel, and I end up with 1 over x. That's actually going to be an important issue in about a month's time when we look at another chapter. Okay, well, knowing that the derivative of e to the x is just e to the x, and the derivative of ln x is 1 over x, we're good to go. Let's try this out with a few examples here. So I'm going to try to do a derivative of this expression. No problem. All right, y prime. What's that going to be? Oh, wow, that doesn't look like e to the x. This looks more complicated. Got a little blob thing going on there. That's all right. We're ready to go. We'll just treat that like it's x, and we'll say, all right, 4, you hang around, and e to the x, you just stay the same. So this will just stay the same, right? That's how e to the x works. But, oh, I was just cheating right there when I wrote that down. I treated -2x as if it was x. So I need to multiply what I just wrote down by the derivative of -2x, which is just a -2. Now, moving down the road, -2 e to the x. Well, the 2 hangs around, and derivative of e to the x is e to the x. So that's -2 e to the x. And then this last one, whoa, that is not the same as what we've been talking about. This is worth clarifying here, right? That's actually an exponential. That's a function that grows extremely fast on its strong side. And this is just a plain old power. We've been playing with powers for a long time. I know what happens. The exponent falls down out front. We're going to have plus e times x to the, then lower this by 1, e minus 1. So a very different approach depending on whether it's an exponential or whether it's a power. The one beside it, that is a product rule. So the derivative, we're going to go and do the derivative of x squared, that's 2x, multiplied by the other one left alone, e to the 5x. Now reverse. Leave the x squared, and then the derivative of e to the 5x. Well, I know that e to the x, it just is its own derivative, and that's just a little blob that's there. So I'm going to say, okay, it'll pretty much look like this. But that was just cheating because I treated the 5x as if it was x. So I need to multiply by the derivative of 5x, and that's just a 5. Okay, wasn't so bad. Same thing here now with this one. Big, huge blob sitting right there. So I'm going to have to go and do the chain rule with this. My derivative, this might get a little long here. Well, e's just hang around. They just are their own derivative. So I'm just going to rewrite what I see. But that was cheating. I just treated that as if it was x, and it's not. So now I need to multiply by the derivative of that pink stuff. And I'm going to put it all like right here. Maybe use some brackets. Derivative of x to the 1/2. No problem. I'll just think of that as a power. 1/2 x to the -1/2. And then the derivative of this minus cos of 2. Oh, another little blob going on right in there. Well, let's just treat 2x as if it's x for a minute. Derivative of cos is minus sine. Got a double negative happening, so plus sine of 2x. But that was cheating. I just treated 2x like it was x, so I have to multiply that answer by 2 and then finish that off. This next one, again, lots of chain rule happening. I know that ln, if I just do its derivative for ln x, it's 1 over x. Let's play the pattern. Derivative here, 1 over. Let's go 1 over that blue blob. Okay, that was cheating, so right away I have to multiply what I just wrote down by the derivative of that blue blob. And that would be 12 minus cos x. And if I just leave it like that, the order of operations isn't quite right. I need to stick some brackets on there. Okay, this one. Let's take a look here. There are a couple of different ways we can do this, including using some ln properties, which we'll do over here. But for now, let's just do this kind of by brute force. So the derivative, well, I see this blob, so I'm just going to treat that like x for a minute and see what happens. I would go 1 over that. Okay, well, that's a bit of a complex fraction, but it's doable. X minus 4, well, sitting on top of 3x. That was cheating, so right away I have to multiply by the derivative of that blob. And that is a quotient rule. Not a lot of fun, but we can do it. So the derivative of x minus 4 is just a 1, multiplied by the 3x left alone. Then subtract x minus 4 times a 3, all sitting on top of that bottom squared. Lots of chain rule happening here. Now, here's a totally different way to look at this. In your math class, you've been shown how you can think of this as ln of x minus 4 minus, division turns into minus, ln of 3x. This might be a nicer approach to take the derivative this way. You'll get something that is exactly the same mathematically. It just might be a quicker way there. So I still do see some blobs, but they're not really scaring me, right? Just a nice little x minus 4 or a 3x. Okay, treat that x minus 4 as if it's x. The derivative of ln x is 1 over x, so that would look like that. That was cheating. You just treated that blob like it was x, so I got to multiply by the derivative of the blob. Pretty harmless, just a 1. Moving down the road, minus, treat that like it's x. 1 over 3x. Multiplied by the derivative of that, just a 3. 3's actually canceled there. All right, example 2. This is a neat example of something that we call an exterior point. This point is not actually on the curve that they give you. It's exterior to it. It's outside it. And you'll see what happens as soon as we kind of do a little quick graph of this. So we're trying to find the equation of a tangent line to this exponential function, and the tangent line has to pass through this point. I'll give you a quick little sketch of what's going on. Okay, let's draw a quick little x and y axis here. All right, this function is your kind of classic exponential, maybe stretched vertically and then lifted by 1. So it's kind of way up here, and then it just does its climb, just like you'd expect. And we're going to try to find a tangent line to that, but this point 0, 1, not on that graph at all. In fact, 0, 1 is, way down here. There's 0, 1. And we're going to try to draw the only tangent in to this graph. There's just one, and it's going to have to touch that exterior point and touch the graph before it wanders away. And I don't know where it's touching that graph. That point is actually a mystery to me. It's not touching at 0, 1, because 0, 1 is exterior to that blue graph. Okay, all right, let's see if we can get this to work. We do know that for that blue graph, the function is equal to 2 e to the x plus 1. And the derivative for that graph, okay, the slope of that graph, let me pick a different color here. The slope of that graph is going to be, well, just 2e to the x. The 2 hangs around, derivative of e to the x is e to the x. Okay, here's the approach. We're basically going to get there by saying the grade 10 slope, just good old rise over run, has to equal the Calculus 12 slope. That's how I like to look at it. So what's the grade 10 slope between these 2 points? This green point and that red point there. I'm literally just going to do y2 minus y1 on top of x2 minus x1. And when I do that, I would end up with y minus 1. Doesn't matter which one we start with, as long as you continue with that pattern. So x minus 0. So that's the slope a kid in grade 10 would get if they connected up those 2 points. What we want to do is say, hey, that's got to be the actual slope of the graph right at that point, where x is x. And I can see that the slope is given by this orange thing down here, 2e to the x. So that has to equal 2e to the x. And if we solve this, we can figure out where this is happening. That's our goal right now, is to find out what is the x value where this is occurring. I'm a little bit troubled by the fact that this equation has 2 variables in it. There's a y showing up in there too. But I do know this. That red point, it's touching the blue graph. I know the green one isn't, but that red point is actually touching the blue graph. So I know that the y's on that blue graph are constrained by this equation. So this is equal to y, this 2e to the x plus 1. So I'm just going to replace that. I'm going to say 2e to the x plus 1. There's my y. Right? If you want, you can stick it in brackets just to sort of emphasize. And then let's keep going. Minus 1, that's that one right there, all sitting on top of x minus 0 is equal to 2e to the x. Oh, this is going to clean right up. What do we got here? The 1's go away. We're going to have 2e to the x sitting on top of an x is equal to 2e to the x. Okay, let's go and multiply both sides by x. And we're going to have 2e to the x is equal to 2x e to the x. Well, I'm going to get this equal to 0 and do a little bit of factoring. If I do that, I could say 0 is equal to, and then do some factoring here, 2e to the x times, you know what, I'm skipping too many steps here. I was just concerned for space. Let me just go over here. There's lots of room here. Saving that room on the right, I'm going to need it. Okay, moving some terms. 0 is equal to 2x e to the x minus 2e to the x. Now I'm going to do some factoring. I'm going to factor out a 2e to the x, and that'll leave behind x minus 1. And I'm wondering, how could that possibly be 0? Got these 3 things all multiplied together. There's this thing, and that thing. So one of them's got to be doing it, or maybe multiple things. Well, the 2 can't be doing it. It's busy being 2. It can't be 0. And e to the x is never 0. It can be awfully small, but it's never 0. So the answer is actually hiding here. X is equal to 1. So I've just learned that this red point that I was just calling x, y, I actually know that the x value is 1. So I'm going to go here now, start working on this thing. I have found, with a little help from the math, that the x is equal to 1. Let's go and actually see what that full point is here. Right, the other point, it's 1 for x, and the y, well, I could put just numbers into this. 2 times e to the 1, that's just e plus 1. So the y value looks like this, 2e plus 1. Okay, nobody said it was going to be a nice number, but there it is. That's the red point. Okay, great. Now, let's see if we can find the slope. I want to know what is the value for that slope at that point. We were doing orange, right? Okay, so slope at x is equal to 1. What is that? Let's go and use this orange function here. Y prime, figured out at 1 for x, just putting the numbers in. Looks like it's going to be 2e to the 1, just 2e. Okay, so you've got everything you now need. You have a point. Actually, we have 2 points. We have this point. We also have this point on that red line, and we've got the slope. So pick either one of those points. It does not matter. And let's do our usual game. Probably will be easiest if we pick the point 0, 1. That's what I'm going to do. So I'm going to say, all right, there's another point out here, x, y. Play our usual game. Y minus 1, all sitting on top of x minus 0, has to equal 2e, has to be that slope. Moving the x minus 0 to the other side, here's the equation of that tangent line. Yes, you could just call that x instead of x minus 0. But that's what I would go with for the equation for that. All right, now our next step for just a minute or so is going to be to look at how we can use exponentials and logarithms to kind of get out of a little bit of a traffic jam. So I've just titled this Plans for 3 Problematic Questions. I want to show you 3 different kinds of things that can come up where you need some plan to get out of. First one, how do I do a derivative of a logarithm that isn't ln x? You know, ln x with that nice little e for its base, that's great. But what if for example, right? What if, you know, for example, somebody says, oh, could you please go and do the derivative of logarithm base 2 of x? You have to go and do the derivative of that. Well, the answer is you can't. So you want to change this to something that you know how to work with. You want to change it to logarithms. So we're going to do the change in base formula. So we're going to change the base to ln x. Ln x is the only thing that works. And here's the formula for that. We saw it back in the first chapter. If you've got some logarithm base a, some awkward number like a 2 of x, you can rewrite that as ln x divided by ln of a. And I want you to rethink this as being 1 over ln of a, that's actually just going to be a number, multiplied by ln of x. There's your algebra. So it turns out, you know, with this log base 2 of x, you could actually rewrite that. In fact, let me just move that for a minute. Cheating on you here, going to move that around. If I had a base 2 logarithm, I could say, you know what, I don't like that. I'm going to write that as 1 over the ln of 2, that's just a number, multiplied by ln of x. Okay, but don't be in any way bothered by this, because that is not algebra, it's just some nice little constant that's there. And so if you had to go and do a derivative now of this thing once we've changed the base, that constant, 1 over ln 2 for my orange example, or just 1 over ln a, it's just going to hang around. It's just a number. And then you would do the derivative of ln x. There's your algebra, 1 over x. So in this orange example, the derivative, yeah, you'd have 1 over the ln of 2, just a plain old number. It's an irrational number, but a plain old number multiplied by 1 over x. So if you have a base that isn't e, get away from it, switch it over to natural logarithms, and then you're good to go. What about the reverse? Well, now what about for exponentials? What if you have something like, you know, y is equal to 2 to the x? What do you do with that? You cannot say, oh, the x comes down, it's x times 2 to the x minus 1. That's for powers, not for exponentials. The only way out to deal with this is we're going to have to do something called logarithmic differentiation. We got to do it at least once so you can see what the answer looks like. Then maybe you can remember it. But here's how logarithmic differentiation works. We haven't tried this yet, so I need to explain it to you here. We're going to take the ln of both sides. Then after that, we're going to do good old implicit differentiation. So it's a couple of steps, but we can get there. All right, let's try it out with this y equals 4 to the x. And again, I'm going to write down something that's not true. Do not follow me. This is completely wrong. You can't say, oh, well, that's just like this, right? No, that is for things that are like x to the 4th, where you have x down as your base. Here we've got x as the exponentials. That's totally wrong. Got to get rid of that. Okay, first thing, take the log of both sides. So that's going to end up looking like this. We're going to have ln of y on the left, and then we're going to have ln of 4 to the x over there on the right. Now, you can rewrite that based on our log rules. You can say, hey, hang on, that's the same thing as x times the ln of 4. Right? So we don't need this. Let's go and write that instead. And I just want to mention that this thing right here, don't be bothered by that. It's just a number. There's no algebra in there. It's just arithmetic. So now we're going to go and do implicit differentiation. Let's take the derivative of both sides. So I do my derivative of ln y. I'm going to cheat when I do that. And I'm going to say that you're going to get 1 over y times, all right, fixing the cheat, y prime. Ooh, that's okay, I want that. And now over here on this side, this is kind of like saying x times 5. You know, if you had this and somebody said do a derivative, you'd be like, that's so easy, it's just 5, right? So it's just a linear term. That's what we have here too. The ln 4 is just a number bumped onto the x. It's just a nice linear term. So the derivative for that's just going to be that number, awkward number, but just that number ln 4. Well, we're just about done. This example, y prime, the derivative, if I solve for y, it's going to end up being y multiplied by the ln of 4. Now, you could leave it like that, but why not go and say, hey, look, here's y, here's y. We could say, well, y is just 4 to the x. So the answer here is going to be 4 to the x ln 4. Now let's just look and see what happened here. We were trying to do the derivative of 4 to the x. And it came out to be 4 to the x ln 4. It'd be an interesting question to say, does that work all the time? You know, what if it had been y equals 5 to the x? Well, it turns out the pattern works. The derivative would be 5 to the x ln 5. We could put any number we want there, including, if you really want to kind of push the envelope here, you can say, what about e to the x? Sure. The derivative would be e to the x ln e, and ln e is a 1. So you're right back to knowing that the derivative of e to the x is e to the x. But yeah, that pattern does work for any one of those exponentials. Okay, what if it looks like this though? What if you have y is equal to 4 to the x plus 3x? Don't take my advice. Okay, if you try to take the logarithm right away, if you say, oh yeah, I'm gonna go and do this, I'm gonna go and do the ln of 4 to the x plus 3x, well, you are stuck, right? You're like, well, you know, now what? Right? And the answer is, well, there's nowhere to go. So don't do that logarithmic differentiation on the whole thing. Instead, just work term by term. We know we can do that for polynomials. We can do that here for this too. So the derivative in this case, think about that 4 to the x. Do the logarithmic differentiation if you have to. And then you say, okay, that is 4 to the x times this number, ln of 4. Like ln of 4 literally is just a number, right? You can say, hey, calculator, what is ln of 4, right? Just some number, 1.38, yeah, whatever. That's the derivative for the first part. Then walk on down the road. Derivative of 3x, well, that would just be a 3. Okay, so that's the idea there. Okay, last kind of problematic thing that you might need to be ready for is, what about something that just looks hideous? Some huge quotient or product like this one here, and somebody says do the derivative. You actually know how to do it. You could do it as a quotient, you know, with a product rule and a whole bunch of chain rules, and it absolutely works. But if you do logarithmic differentiation, it actually works really, really well here. So that's what I want to try. I'm going to go and do the ln of both sides. I'm going to go and do the ln of y, and I'm going to go and do ln of that really awful thing, okay, that big, huge, ugly mess. All right, now let's make that right-hand side a little nicer. The left-hand side's fine. We'll just say, yeah, we're going to do the ln of y. Great. Now, log properties. If I was doing, you know, the ln of this, I can start using my Math 12 logarithm properties to break this apart. And I know that products turn into addition, division turns into subtraction, and exponents just turn into multiplication. And so I could write this in a much simpler way, like this, with a whole bunch of lns. I could say, hey, that's the ln of this. That's the ln of x plus 1 all to the half. And I could even bring the half down. Maybe I'll do that on the next line. And then plus the ln of 2x minus 1 cubed, right? So multiplication turns into addition. Division turns into subtraction. So the ln of 3 x to the fourth. And also dividing by the ln of x minus 1 squared. Okay, more Math 12. Not really doing any calculus yet. This half could come down. So the ln properties just make this a little bit nicer, a little more manageable to work with when we go to do a derivative. I could actually play around with this and break that up as the ln of 3 times the ln of x to the fourth, and then bring the 4 down. But this is pretty harmless just as it sits, so I'm not too bothered by that. I'm going to let it sit there. But I am going to bring this 2 down. Minus 2 times the ln of x minus 1. Okay, now we do our implicit differentiation. So I'm going to do the derivative with respect to x of both sides. Over here, cheat like crazy. Just say, well, if it had been ln x, I would have written 1 over x. So let's write 1 over y. That was cheating. You just treated a y like it was x. So we'll have to multiply by a y prime. But that's okay. We want that thing. I'm happy it's showing up. Now this side. All right. If it was just ln x, right? I mean, what we've seen today is that if you do a derivative of just ln x, you get 1 over x. Well, I got some blobs going on here. This half is going to hang around. And then I'm going to have 1 over x plus 1, and then multiplied by the derivative of that x plus 1. That's just a 1. Moving on down the road. The 3 hangs around, times 1 over 2x minus 1. Oh, that was cheating, and the derivative of that is a 2. Now here, minus. All right, well, that'll be a 1 over 3x to the fourth. And then multiplied by the derivative of that, 12x cubed. And that reduces quite nicely. And then the last one, minus 2 times 1 over x minus 1 times the derivative of that blob, just a 1. Okay, we're basically there. What I'm going to do now is just move this y to the other side so that I can actually say, hey, y prime equals, and then I'm going to write down my answer for that. Instead of just writing a y here, so don't follow me for a second, instead of just writing a y, this is 1 over y as it moves, and then like all that stuff, well, the y was actually what we started off with. So if y equals all that stuff, it's time to write it down once. Right? So here comes my y. It is the square root of x plus 1 times a 2x minus 1 cubed, all sitting on top of a 3x to the fourth, x minus 1 squared, right? So all of that, that's just the y. And that gets multiplied by all this green stuff, right? So times, okay, maybe we'll tidy the green stuff up a little bit. A little bit. Here, yeah, we can put the 2 and the 3 together and call it a 6. This can be cleaned up. That's actually just going to be a 4 over an x. And then the last part, 2 all over x minus 1. So that can be a little technique to use logarithmic differentiation to your advantage, just to make it a bit nicer. So you don't have to do an awful looking quotient rule. It's just an option. Okay, before we hit the last page, just doing some last little practice, let's kind of summarize what we know so far. The derivative of e to the x, it is the only nice exponential. Its derivative is exactly itself. The derivative of ln x is 1 over x. And something kind of for later on in the course, the derivative of ln of opposite x is also 1 over x. That'll be important later. If you have to do the derivative of a logarithm that isn't a ln, like log base 2, well, we found that when you do the derivative of that, you could rewrite the question. You could say, hey, this is like saying, please do the derivative of, and then you rewrite their question. You say, oh, that's actually just the ln of x, because I want to do that one, divided by the ln of your awkward base, just a plain old number. And we found in the end, by the time you were done, you do the derivative of that, and that plain old number just hangs around, and then you get the 1 over x. If you've got another exponential that isn't an e to the x, what we saw was the derivative, it is a to the x. It's kind of like what you see here, but with an extra little correction factor multiplied by the ln of that base. And the derivative of a power, wow, we saw this at the very beginning of the chapter, right? So just kind of going back, if the x is down in the base, okay, this is old news to us. The a falls down, x to the a minus 1, right? That's old news. Okay, with that new knowledge all summarized there, let's try this out with just 4 more examples. Got to do this log base 2 of some awkward blob. Yeah, don't really like that. Okay, but there's that blob in there. All right, the plan. Well, let's look back. There's one page here. If I'm doing a log that isn't an e, I end up picking up this correction factor of 1 over the ln of that awkward base. And here that awkward base is a 2. So my derivative here, I'm going to have y prime 1 over a ln of 2. That's just a number, some awkward number, times, now let's play the game. Treat that blue blob like it's x, so you're going to get 1 divided by 2x to the 5th minus 8x, but that was cheating. You just treated that blue blob like it was x, so right away you have to multiply by the derivative of that blue blob, which would be 10 x to the 4th minus an 8. Next one, got an exponential. At least it's an e. I like that, but it does have this exponent that is not an x, so we'll fake it. And we'll say, okay, the derivative there, it's going to look just like the original function, e to the 4x minus the cosine of x squared. That was cheating. You just treated that blue blob like it was x. So right here I have to multiply by the derivative of that blue blob. That would be 4 plus, okay, chain rule again. Right, it's going to be plus because when I do a derivative of cos, I get minus sine, so a double negative. I'm going to have sine of that x squared. That's cheating. Little correction with the chain rule here. And some brackets for good luck, just to get that order of operations feel just right from the chain rule. Whoa, what is going on here? What is going on here? There's x's and y's all over the place. Like, look at that y up in the exponential there. Okay, new deal. This is not nice. This is an implicit relation. We're going to have to do implicit differentiation here. Here goes. Okay, doing my derivative on both sides with respect to x. I'm going to have 2 times, now the derivative of that, a little blob going on there, 1 all over 7 minus x, multiplied by the derivative of that blob, which would be a minus 1. Okay, moving on down the road, plus e to the, okay, weird, little blob there. Well, let's just treat that blob like it's x for a minute. I would have e to the xy, but I now need to multiply that, because that was cheating, by the derivative of xy. That's a product rule. Okay, derivative of x is a 1, multiplied by the y left alone, plus leave the x, and then the derivative of the y. Okay, so that's finally showing up to the party. All right, that is the derivative of the left-hand side, and now the derivative of the right-hand side, another y prime. Yeesh. We have to get those y primes together, all on the same side. We can do that, but to make that happen, we're going to have to do a little distribution. So that distributes onto here, and that distributes onto there. Then we can get this to work. Okay, if we do that, let's think about all the terms that are going to have a y prime in them. We'll put them all over here, maybe on this left-hand side. So y prime, you're going to get bumped into, all right, well, this term, there's an x e to the xy times that. And then this y prime comes over all by itself, and I'll do some factoring, so that would be a minus 1. Okay, now all the terms that don't have y's, they all need to go to the other side. There's this one. It's a minus on this side, so I guess it'll be a positive over here. And then this other part of the distribution, by then it would be a minus y e to the xy. Okay, hey, this is not going to look pretty, but that's okay. Probably only going to need it once. Y prime. This is going to look awful. The top is going to have fractions in it. It's going to be 2 sitting on top of 7 minus x minus y e to the xy, all sitting on top of this binomial x e to the xy minus a 1. Ugh. Usually you only have to use that once, right? So let's just walk away from it. Last one. Wow. Got to do a derivative of this. Getting ridiculous. Okay, I think we can pull this off. Derivative. I've seen what happens with 2 to the x. You know, if I need to, I can go and look back. If I'm doing an exponential that's not an e, it does give itself back, but it picks up this ln of the base. So the first part here, that's going to be 2 to the x multiplied by a ln of 2. Okay, not so bad. Then minus, and now here comes something that's probably going to be some horrific looking quotient rule. Let's get ready. All right, derivative of the top. You got a little blob going on there, right? So we're just trying to dive into this layer by layer. We're going to have 1 on top of that argument, x minus 3, multiplied by the derivative of that blob, just a 1. That gets multiplied by the bottom left alone, times the tangent of 2 root x. Okay, great. Now, minus, oh, I hope I have enough room here. This is going to get ugly. Okay, leave the top. Ln of x minus 3 times the derivative of the bottom. Eek. Okay, I cannot get this to fit nicely, so I'm going to make a change here. Sorry about this. If it will let me. 1 second. Okay, kind of fought me a little bit, but I think we can do this. All right, my derivative, that minus, and then a little word wrap. I need more room. I just need more room for this big, huge quotient rule that's coming. That should be enough space. Okay, so what did we do? We did the derivative of the top times the bottom minus the top times the derivative of the bottom. Tangent. The derivative for tangent is a secant squared. That's if it's just a tan x. This thing is not so nice. Well, we'll fake it. So we'll go secant squared of that argument. That was faking it though. Now I have to multiply by the derivative of that purple stuff right here. Okay, well the 2 hangs around. and then x to the 1/2. The 1/2 would come down, x to the negative 1/2. Now divide all of that by the bottom squared. So we're going to have tangent squared of this 2 root x. Yeesh. Hopefully you only have to use that once. You put some nice value in, like, oh yeah, x is equal to 1. But I'm going to let that sit just right there. And that is the last example for our day on logarithms and exponentials. I'm just going to go back for 1 second just to this page right here. So the key things we learned: derivative of e to the x, it's just e to the x. And the derivative of ln x is 1 over x. And then we got a couple of other little exceptions there down below. And that'll finish this lesson up.